With our knowledge of speed, velocity, scalars, and vectors, we're going to proceed into 4.2 graphs of motion. And today, we're going to talk about specifically position versus time, also sometimes known as distance versus time graphs. Your learning goals. Now, there are three, and I want you to write down all three, but we're going to be working on all of these and maybe a couple others for the next few videos. But I want you to be sure you can construct and analyze graphs of position versus time. And speed versus time we're actually going to get to in another video, so just position versus time is important for this one. Also, recognize and explain how slope of the line is describing the motion of an object. We've already talked about that in class. We've already played with that a little bit in class. So it'll be a little bit more review in this. And explain the meaning of constant speed. So what is constant speed? I'm going to start with that. Constant speed, and you can see it in the word constant, is speed that is always going to stay the same. Speed that does not change. And it's important to understand that because speed is a scalar. When I say constant speed, that means only the magnitude is not changing. So if you were to walk and maintained a speed of, say, 1 meter per second, and you kept moving around, you were going up, down, left, and right, and you stayed at 1 meter per second, you would have a constant speed. What's interesting, though, is you would not have a constant velocity. Remember, velocity is all about direction. So if I were to say that I moved 1 meter per second to the left and then 1 meter per second to the right, my speed would be constant. But because my direction changed, I had a change in velocity. We'll describe this more in class. So an object moving at a constant speed on a position time graph always forms a straight line. Let's take a look at an example. For this, you can just jot down the data table, and I'm going to have a graph as well, so please jot down the data table and the graph. If you'd like to jot down those bullet points, you can. But looking at this, this is the data for position and time of a runner. And the data is showing us the runner took 10 seconds to run each of the segments. So at time 0, he was at position 0. Time 10, he was at 50, 20, 100, 30, 150. Now, if we were to take this and put this into a graph, this is what it would look like. I'd like to point out, first off, I've got all four things there: title, labels, plot, and scale. Moving on. What you can see is that time 0, 0, time 10, 50, as we said it a second ago, but it's plotted out a straight line. It's not a line that's curving up and down, moving. It's a straight line, straight diagonal line, moving away from the origin. A straight line on a position time graph represents constant speed. Now let's take a look at that a little bit more on the board. So I've very roughly drawn out that graph again up here on the board. I'm going to stand over here to show you again the runner's position versus time. And just want to point out again, we have a straight line, so that represents a constant speed. Constant speed away from the origin. What I want to do is just walk us through slope again. Remember, slope, what is it? Think for a second, think for a second. Slope is rise over run. And remember, from what we did in the walk, jog, run lab, that the slope of the line you guys figured out was speed. The rise is position, we're just going to call it distance, divided by the run, which is time. So slope on a position time graph or a distance time graph is the speed. So let's just figure out, what was this runner's speed? Again, to calculate slope, you need rise over run. So you have to pick an x1 and an x2, a y1 and a y2. Pick two coordinates. When you have a straight line, you can go top to bottom, but I'm just going to pick the middle two. So here's my one coordinate at 10 seconds over. comma, 50 meters up. Here's another coordinate at 20 seconds over, 50 meters up. So a rise, which is the distance one, is going to be, it went from, oops, sorry about that, 50, should be 100. A rise, it went from 50 to 100, so it's 100 meters minus 50 meters. Y2, the second y, minus y1. And our run is x2, the second x minus x1. So 20 minus 10. 20 seconds minus 10 seconds. Notice I left the units in because those are important. So we get 100 minus 50 is 50 meters over 20 minus 10 is 10 seconds. And this is going to get us with 50 divided by 10 is 5. Units carry over, meters per second. There you go. That is the slope of the line. The slope is 5. The speed, which is a constant speed, is 5 meters per second. And we'll talk about how this relates to velocity as we move along. So let's take a look at another 2 examples, and then we'll work on this more in class. All right, what would it look like on a position time or distance time graph if a person or an object wasn't moving? They were just standing still, not going anywhere. Let's take a look. Now, I'm going to abbreviate this as a D and a T down there. Now, what you're allowed to do when you're just hypothesizing or thinking things out and you don't have physical data, it's okay to write graphs like this, where you just label each axis with the variable letter and just have the axes. When you're just trying to conceptually think out what it looks like. If you have data, you got to go through the steps. You need your title, you need your numbers, you need your all that good stuff. You need it. For this, it's okay. So if a person is not moving, what would that look like? Well, let's say that they're away from the origin, somewhere maybe like 5, 10, I don't know, away. Second lunch. They're away. Say they're right here. Where would they be at time 0? Well, they'd be right here. Where would they be, I don't know, a minute later? They'd still be right here. Where would they be a little bit later? They're not moving. They're still going to be at the same position. What about later? They're still going to be at the same position. So a person or an object not moving is a straight horizontal line on a position time graph. Now, is this constant speed if they're not moving? Think about it for a second. Remember what I said constant speed is. On a position time graph, it is a straight line. I didn't say anything about it being sloped or flat, I just said it's a straight line. Is this a straight line? Yes. And if you think about it, this person would be going a constant speed of maybe 0 meters per second, or maybe 0 miles per hour, or 0 kilometers per hour. They're maintaining a constant speed of 0. So this still counts as a constant. 0 speed. Not moving. If they weren't moving and they were at the origin, it would look like this. If they weren't moving and they were somewhere in between those two, it would look like this. Flat line. That is your constant speed, or a constant 0 speed, not moving. One more example. So what would it look like if now a person was moving towards the origin with a constant speed? So I'm assuming that they are somewhere away, some position or distance far away from the origin, and they're going to make their way back to 0. Well, let's see. Everything always starts time 0. If you're away from the origin, where are you going to be on the y? You're going to be here, you're going to be here, here. You're going to be somewhere up away. So let's say you start here. That's your starting position. Where are you going to be after a little bit of time? Well, if you're moving towards the origin, you're going to be a little bit further down. You're going to be maybe here. As time progresses, what are you going to do? Maybe you're going to move a little bit further down. And if you're going at a constant speed, it's going to have to be in a straight line. And then as time goes on, you're going closer and closer and closer to reaching your original origin. And check that out. So this is what it looks like if you were to move towards the origin with a constant speed. It's basically just like the other graph that we did, that first graph, but instead of the line going up, the line's going down. It's still a straight line, which means a constant speed. What does this mean for slope? Well, let's for a second imagine that these had the same numbers as that first example. This person maybe started at 150, got down to 0, and then it took them, in the same example, from 0 seconds all the way to 30 seconds. And then they had maybe the same points in between. They also were at time 10 seconds, they reached 100 meters. And by maybe time 20 seconds, they reached 50 meters. So reverse of the first example. What would the slope be here? Well, let's take a look. Slope, rise over run. First, what is the rise? We went from 100 to 50. This is our y2. This is our y1. So it's 50 minus 100. It's going to be in meters. Over, we went from 10 to 20. So this is our x2. This is our x1. 20 minus 10 seconds. You noticing something different? So 50 minus 100 is negative 50 meters. 20 minus 10 is 10 seconds. And this gives us negative 5 meters per second. So when a line's going down towards the origin, we get negative numbers. When it's going up away from the origin, it's positive numbers. Did the number itself change? Did the number of units change? No. What is the only thing that changed? The sign. Maybe it's telling us the direction. Maybe that has something to do with velocity. We're going to talk about this in class. Positive and negatives, as we've said before, are going to be important for understanding which way objects are moving. So that's going to be it for now. I'll see you guys in class.